Okay, in the last video, I did an overview of EMG. In this one, I want to go a little bit more into some of the um, more details of EMG. First of all, I should mention that what we were talking about, or what I'm talking about, is surface EMG. And that's obviously putting the sensors on the surface of the skin. There's another type of lead that is called an indwelling EMG, and that's where you actually stick needles in the muscle to try to get a little closer to the muscle fibers. I actually have not done indwelling EMG. It is it is a different instrument, but it is still EMG, and you're getting a little bit more of a finer perspective of muscle activity. Now, remember, you've got these muscle fibers running along here, and we're putting our sensors for surface EMG up here. These muscle fibers run the length of the muscle. And we're putting two sensors there, and then we maybe put, and I know this is not how your systems are working now, but the concept is important. Then you put a third lead, and really what you're doing is you're looking at this signal, and you're looking at this signal, okay? Now, an indwelling lead, you actually stick needles inside, and what you're trying to do is get a finer perspective, and while you're getting through all the fat in the skin, you're getting rid of all that interference, and you're trying to get how active muscles are in a real narrow area. Surface EMGs is looking at a little bit bigger area of muscle activity. It's not really hard to actually know how much volume we're actually getting, but I tend to think of the systems that we use getting about a centimeter cube volume of space for EMG. This is going to be much finer, and I don't know what this is, but it will be much more intricate around where the leads are indwelling on the muscle. Now, remember, I showed you the voltmeter, and this signal is really small, okay? Really small. So you need to amplify the signal. Sometimes you put the amplifier close to the lead, and you amplify down here, near as close to the lead as possible, because this is such a small signal. Anywhere else, you're actually, we're getting bombarded by this electrical wilderness that we live in, where all these electromagnetic waves are hitting us from all different sources. And so these are, in essence, these wires are, in essence, antenna. So if I put my amplifier all the way back, at the end of the wire, then the signal may actually get degraded and get infected with all this noise. And the noise may be a bigger magnitude than the actual signal. And that can be a problem because we sometimes have a hard time distinguishing the signal when the noise is that large. The advantage of having the amplifier all the way back here is that these leads are very small. They have very little mass and therefore very little inertia. And a disadvantage of having the amplifier near the lead or with the lead is you give this unit more mass, which means this unit can start moving, all right, when you're moving or when the person's moving. And if you start to move the leads, you can probably envision that the skin, which is elastic, and the tissue underneath it can shift back and forth as well. And that can actually cause noise in the signal because you're actually moving these leads around. And just like when I was trying to hold the leads and measure the battery voltage, if I move the leads a little, I'm getting a different voltage simply because I'm not getting the same connection each time I move those leads. Well, the same problem exists here, and we call that movement artifact, where we start to pick up electrical signal that's more associated with movement as opposed to electrical activity. They mean that we're actually measuring muscle activity in different spots of the muscle. Muscles like the bicep, we may put our leads in one spot And then as we start going through contraction, the skin actually shifts, and we may actually be recording muscle activity in a whole different area. So that's a problem, okay? But it's a problem that we need to understand so that when we're processing our data, we're trying to make good decisions when processing. And ultimately, we need to understand all these limitations and when interpreting EMG. All right, so we get a lot of electrical noise from I call it the electrical wilderness. It's not actually my phrase. It's actually a book I read years ago, Wilderness. Okay, noise from the electrical wilderness. We're getting bombarded with all this. And I can tell you stories about measuring EMG and getting a lot of noise simply because of other electrical devices that were either plugged in the same plug or you grab the rails of a treadmill and all of a sudden you're just catching all this electronic noise that is out in the wilderness. And then we're also getting noise from movement of leads relative to, come on, 1O, to muscle, okay? And this movement, there's lots of things that will cause the movement artifact or movement, the noise due to movement. One is, as I mentioned, if we have too much mass for the sensors, that can actually increase the amount of movement artifact we may get. But then it's how tight we strap the EMG leads down to the body or onto the skin, how well our glue or our adhesive is working for the pads that you put on the skin and ultimately the leads. So we really want to watch for these two sources of noise when we're doing EMG and try to reduce them as much as possible. Okay, so now let me tell you why I keep drawing 3 leads here. Okay, and one of the EMG recording approaches is to use what's called common mode rejection, CMRR, common mode rejection, and actually it's a ratio that we ultimately talk about. But it's a common ratio, not ratio. Common mode rejection. I'm going to explain it here, and then later on I can do a video based upon some Excel data to show it a little bit better. I'm going to do my same 2 leads here. Okay, and I like to put these leads as close as possible as I can on the surface of the skin, because remember, the concept is I'm trying to measure the same action potential under each lead. And so I'm just going to draw one action potential coming along here. Okay, I'll just do it like that. This would be time 1, and it's picked up by this sensor. Then later, the other sensor is going to read the same action potential. Same action. This is the concept, okay? Potential. And everything on EMG is sort of predicated on this. That's the recommendations to put your leads in line with the muscle fibers. That's why you do that. You're trying to measure the same action potentials, and really it is plural, because we're not just measuring one action potential here. We're measuring hundreds, if not thousands, of action potentials. Okay, and that's why our EMG looks the way it looks, is because we get lots of electrical activity from a lot of different muscle fibers. All right, so we're trying to read this lead, or excuse me, this signal at this moment in time, and then the same signal at another moment in time. What we're going to do is we're going to look for anything common at any one moment in time. So what's going to be common is any electrical noise coming in and being picked up by these leads, okay? Anything common at any moment in time. So what we end up seeing is something like this. So if I draw the 2 signals, we're going to put time down here. And I'll put voltage over here, okay? And all I'm going to do, I'm going to draw one, I'm just going to draw it as a sine wave. It's easier to draw. And this is lead one, okay? And it's recording, lead one is recording this signal as it passes underneath it. Remember, innervation zone is over here. And then, so this is lead one. And then at some moment later in time, because of the way I've got my other lead set up here, that action potential passes under that lead. So I'm going to draw it the same way because it's the same signal. That's the concept. But now it's shifted in time. It's over here, okay? Because this lead is moved over to a different spot. All right, so now what do we do? Well, when what your EMG system is doing for you is it's actually giving you the difference between these two signals, okay? It's calculating the difference. And by calculating the difference, it will take out anything that's common at any moment in time. So what do? We just draw a line down here. And at this moment in time, whatever time it is, time I, the system will calculate the difference between these two. And then at this moment in time, Ti plus 1, all right, it will calculate the difference. And interestingly, if it's the same exact signal, or the same signal, we'll actually get the same signal over here at the end of the day. That's what you're going to see. Now, why do this then? Well, what you're actually trying to do is get rid of any signal that's constant, okay, between these two leads at this moment in time. So let's do a little bit of math. And what I'm going to tell you is this noise is what's constant at this moment in time and at this moment in time, because this noise is happening as this whole thing is going on. And I'm doing electrical wilderness noise. It could be other sources of noise too, but electrical wilderness noise is the most common that we're trying to get rid of with this process. Okay, so I've got the two signals. Let's say that lead one is measuring voltage. We'll do a 1 here, plus some noise, okay? We'll just call that N, all right? And then let's do lead 2, and it's going to be the voltage at lead 2 plus the noise, and I should put this is at time I. This is at the same moment in time, okay? And what you're going to do in a common mode rejection process is you're going to take the difference of L1I minus L2I. And that's going to give you your common mode rejection. I'm not going to do it as a ratio at this stage, okay? I'm just going to call it common mode rejection. Let's just do our algebra here. V1I plus N minus V2I plus N. Now remember, this voltage is different than this voltage at this moment in time because the signals are shifted, okay? The signals are shifted. So I'm getting different voltage. Even though it's the same action potential, it's just shifted in time. So I'm just looking vertically here at this moment in time. Now you can see, just looking at your algebra, what's going to happen. I just drew my algebra here, and my noise, my common noise at this moment in time I is removed. And I end up with V1 at this moment in time minus V2 at this moment in time plus N minus N. It's going to get dropped out. So the noise, the common noise is removed. It's a really simple process. And ultimately, if we continue our algebra, and I'll show you this in Excel, we will actually end up, if these two signals, these two signals are identical, you'll actually, by taking the difference, you'll end up with the same signal. Um, for, all that's going to be different is any noise that's overlaid in the signal will be removed. So the common noise is removed. Okay. All right. So what's important about this? Well, one, that's why you have, that's why your systems will often have 3 leads. Now, the way that some systems do it, and I'm not sure if Cometa is this way, I don't know, is that it may alternate which one of these is the ground. And so it does sort of a trick on us in that it will switch back and forth in terms of which lead is a ground. All right, it's just an electronic trick. But in the old days, we would actually place the ground in a period where, or in an area where there's very little electrical activity on the body. So we would put it on a bony landmark or a tendon. Now, but again, the electronics have gotten a little bit more sophisticated where this ground has slowly moved back closer to these leads, and the ability to detect the voltage has gotten a little bit finer, and therefore the common mode rejection process is a little easier. That this lead is just, this ends up being one set of units. You can actually buy a unit that looks like 1, 2, 3 sensors, okay? And you put that sensor, and this may actually be the real size of the sensor, about 1.5 inches long, and it will do the common mode rejection using 3 leads. If it only has 2 leads, then what it's doing is in the internal guts of the instrument is just switching back and forth which lead is in essence the ground. Okay, so that is common mode rejection, and I didn't do the ratio part, but that's okay. We're just going to do, I really want you to understand that the concept here of the rejection of common noise. And that common noise is electrical noise that we're getting maybe through a wire. Maybe we have a bad ground for a computer. Maybe we're getting some electronic noise through the system itself, or we're getting electronic noise from the environment. Okay, I think that's it for this 1, 2, and 3. Okay, thanks everybody.